Hello, guys. Welcome to the part two of the system design of the proximity service like Yelp. Um, if you are following the previous video, you know that where we left off in the last part was we have been trying to design how exactly our database and the data storage would look like. So there we have been discussing about the geohash, and we also explored some of the very basic coding like uh, how easy it is to convert a certain location to geohash and how exactly we can query on top of that. So that is where basically in any kind of proximity service, that is the very ideal database for the systems where we are trying to find some nearest, like some nearest location. Suppose something is within like 2 mile radius or 10 kilometer radius. So Redis geohash give us this extreme flexibility to write queries like this if we are storing in the geohash tables. But let's talk about some other modules as well, or the other models of the data storage that we can do while we are dealing with location data. So for this particular use case, we have been doing proximity service, right? Like if there is a certain point where the user is sitting in. Suppose this is a certain point, then within a radius, if how many other things are there. For example, within the radius there are like 1 2 3 4 5 6 businesses are there. Okay, so suppose these are some businesses, and what our API will do is our API will return this. Now let's explore some other models as well, so like Quadtree and Google S2. And then at the end of this video, we will try to see how what exactly is the use case for each of them. Like there are organizations which are using Google S2, like Uber, and there are government agencies which are using Quadtree. So in what use cases they exactly use it. And just a disclaimer, this all things, like when we are going to discuss about Quadtree or Google S2, they belong to completely separate domain of computer science, of computational geometry, and it is really very heavy topic. Like if we have to understand the maths, how Quadtree or Google S2 calculations are being done, that will be a really heavy topic to explore. So what we will do is we will on a very high level see, we will take an example data sheet, and based on that data sheet we will try to see how the data is being stored and how the data is being retrieved. And retrieval means like how exactly we can query on a certain given cases, and then we will come around the real life use cases and the trade-offs. So let's talk about yeah so let's talk about Quadtree at first. So before taking Quadtree, let's take a example data set. Okay, so when I say example data set, we'll take some kind of business of some kind of a business data, suppose from Mumbai. So this particular example data set, what it does is this is going to like mm, around Mumbai, few of the famous eateries or restaurant, I would say. Here you can see like we have given some latitude and longitude. Now these businesses are spread across the Mumbai, and how we are going to plot it. Like if you remember geohash, in geohash what we were doing is uh, we were dividing the quadrant, and in each quadrant we were going really deep and converting that quadrant's position to a base 32 number, base 32 binary encoding. So here we are not going to convert any do any encoding or anything, but what we are going to do is, suppose there is a location. Okay, suppose there are some 200 meter of square area is available with me. So what I'm going to do is, so I'm going to take a basic node. So this node represent this 200 meter. Okay, so when I say node, it is a 200 meter, or rather 200 miles. Let's take it. 200 meter will be too close. So this 200, this is like 200 miles, and then I'm going to divide it into, in my tree, into four different areas. That is, one is the northwest, one is the northeast, the next one would be the southwest, and then another one would be the southeast. Okay, so we are going to divide it into this four location, and again, each of this location, for example, take the northeast. What we are going to do is, we are again going to suppose they have some kind of a like, it can be 50-50-50, or even like a little bit more distributed, like 40-60 sort of a thing. So just for the sake of simplicity, suppose we are taking it into a four equal quadrants. Then what we will again do is, we will try to divide each area into again like similar to this four locales. Okay, so again, like if there are enough businesses here, suppose within 200 miles we will keep a certain, we will keep a certain number, like 100 business. If it is going beyond 100, we are going to divide it. Suppose again in this northeast region, there are like, it itself might be having some 120 business. Suppose here we have 500 business, so definitely the 100 is our limit. 100 is limit for each node. Then we are going to divide everything into like 30. It can be, this one can be 90, and this two can be even 00. So no further yeah, this one can be 00. So no further division will be required from here. So as you can see, like, this is basically how we are going to create a quad tree, and the reason it is being called quad tree, because we are going to divide it into four parts, like the northwest, northeast, southwest, and the southeast. So in this way we are going to store all the data on the, on actually on the leaf level, but again we are not going into that extreme detail. But still I will tell you what happens is, like, the this quad tree will be recursively divided into the northwest, northeast, southwest, and southeast, and then starting from that bounding box, if there is like, suppose here are, as I was pointing, suppose here we have some 600 business, and here we have some 50 business. So we are not going to divide this one. But suppose here on the northeast we have some 350 business. Then in that case we are definitely going to divide our we are definitely going to divide that particular bounding box into again four different location. Okay, so there will be of course latitude and longitude are the bounding box of the latitude and the longitude will be defined over here. Okay, so what the each node will store. Now let's talk about what will be the storage model. Like this is a tree, right? So in the quad tree, what will be the storage model? So storage model is, each node that you see, each node it will have the lat and long range. Okay, what is the highest latitude and what is the longitude that it can hold. Then it will hold the list of the businesses, and of course like it will be holding the pointer to the child node. So now uh, how it will become is, if you see, I'm just taking you one example of some US area. Let's zoom in and try to see. So here you see there is unequal distribution of the data, right? So here this regions doesn't have much business, but the area of the Denver that you see, like the Strasbourg doesn't have much business, but the area around Denver, it has so many businesses. So there will be a way more dense tree around this area. So suppose each leaf here contains approximately 100 business ID, and the time complexity of building this node will be somewhere around n log n. So the main challenge that you can see over here is whenever we are adding any business. Now this is a very important point, because so we are building a tree here. So any new business that gets added, tree needs to be rebuilt. This is the biggest flip side of quad tree. So anytime we are going to add a new business, the tree needs to be regenerated, right? Like suppose for example, if the tree is not exactly in the leaf level, the tree like any new node has to be introduced, like not in all the cases, but whenever like extra business is being added or something is happening there, the if the node structure changes, then what we have to do is we need to rebuild the tree. And the problem that happens in this is, so suppose like building a tree is again a costly process. So if you have like millions of businesses, so like millions or billions of businesses, so building the whole tree with data can take up to, like based on the computational power, can take up to 1 hour or so. Now this is an expensive operation, right? So what we have to do is, like in this kind of cases, again going into a little bit of DevOps side, we have to do certain kind of a deployment to make sure that okay, we are serving although the new tree is being generated, we are serving the data from the old tree. And when the and we have to find a sweet spot where we can actually replace our old tree with the new tree. So some kind of a canary deployment we might need to think over here. Again coming into the details of the maths, how the whole tree is being built, we probably do not have to go there. Okay, so that is not exactly necessary like in our purpose, unless we are studying computational geometry. So just what I would want you to take as a outcome of this is, so if we are having a number of latitude longitude, we can just do a bounding range, we can create a bounding range around that, and we can just try to see how that bounding range is being divided into different location grid. Okay, so that is the very basic points. And the of course the advantage is, like you can just keep on querying over there, like querying a certain area is nothing but traversing through the whole tree, right? So in that case it is a very useful data structure, in few of the real world cases, which we will come just after covering the Google S2. So let's talk about Google S2. So Google S2 is become very popular once like Uber started using it. So now let's talk about what happens in Google S2. So again, like if I see our Earth as a certain sort of a sphere, like this is it is not a round, right? So it is divided into six primary faces of a cube. Okay, so if I have to bring like a image representation of it. So this particular image that over here you see, what Google S2 does is, the Earth is getting divided into six primary faces of a cube, the whole Earth, and then each face is subdivided into a hierarchy by Hilbert space filling curve. So the mathematics behind for Google S2 is Hilbert space filling curve. Again, this mathematics is completely like when we are designing a system, we can keep it out of the equation because this is already been a developed library, and there is a developed proforma to that which we have to follow. So for example, suppose we take the suppose we take a certain latitude from this example, Marine Drive Cafe. Okay, so whatever the data it has, so let's take Marine Drive Cafe. Okay, so the lat long whatever we have for this Marine Drive Cafe, what we are going to do is we are going to have a S2 cell ID for that. So like in the Hilbert space filling curve mathematics, we are going to pass this lat long, and we are going to get something like a very long number, something with root 8 something. I do not really know what will be the exact number, but something around that. And depending on the cell level, this cell ID will be presented on uh, on a tabular fashion, or in a NoSQL fashion, however fashion you want to. Now uh, each business, for example, Marine Drive Cafe will be associated with this business. Now, because it is being converted into a certain mathematics of Hilbert space filling curve, so what will happen is we can very easily do range queries around this. Okay, so the range query means suppose like within 1 kilometer radius, within 1 kilometer radius, how many cabs around me. This kind of range query can be returned very easily over here. Now, why it shines on top of geohashing? Because geohashing, like the moment it goes into the towards the north poles, like around Norway, uh, while Google at first trying to implement this, I was reading in a few of the engineering documentation that they found there is a lot of distortion happens, and that distortion percentages is a lot. And here, because like in Google S2, we are dividing instead of flattening the earth, we are dividing into a curvature. So it gives you a way more better results. Again, why and how? Probably for that we need to delve into the computational geometry, uh, computational geometry calculations. So that is for the time being I'm keeping out of the scope on this discussion. Now, uh, as each cell you can see like representing each of the businesses. So anywhere that I am sitting, so like suppose the user will have a certain cell ID, and finding all the location around the cell ID with a given precision is very easy here. Okay, now so S2 provides this completely spherical cap, and there are like if you explore the functions that any S2 library gives, you will see like it will give you a lot of desired precision. So in case you are seriously building any kind of application which is across the, which is where the customers to be served across the globe, then maybe Google S2 is a very good service that we can use. uh, so now coming into the real life use cases. Okay, so Quadtree, when we were talking about like any GIS system, so any mapping software that you see, where like the l- where we are doing things like spatial indexing. Okay, so while government issuing land or doing some kind of research, so they do this sort of things like spatial indexing. And even suppose two two given object is coming close to each other, so on those kind of cases collision detection can also be done using our quad tree. And also like one very important application is the game development. So suppose in case of the GTA Vice City, right? The whole how the whole map is being stored inside the application is in Quadtree. So what happens is, suppose you want to go to the, like you are driving a car and you want to go to the nearest nearest bar of that particular location. So in that case, the quad tree of that GTA within the game, it helps a lot. So these are the very two popular real life application of quad tree. And now coming to Google S2, of course, like Uber is there, and what Uber can also do is using quad tree is identifying the high demand regions. Okay, so not only through the GPS, but with a proper curvature, it can understand the region where currently a certain high demand is going on, or some natural calamity is going on, so that Uber can mint out some money there from the customers. And even for understanding the weather patterns, uh, even for understanding the weather patterns, Google S2 is very, very useful. So now, in conclusion, both Quadtree and Google S2 definitely are powerful tool, but it is more towards the spatial data management, like where you want to find some weather around the region, or some kind of a map within the game. Quadtree excels in a lot of precisions, and whereas Uber or the other kind of the ride hailing services, they tend to use uh, they tend to use mostly Google S2. Now coming to our now coming to one of the low level implementation of, suppose you are low level implementation of proximity service. Now we know that although we have discussed Quadtree and Google S2, but we know that we are going to use Redis GeoHash, right? So let's talk about Redis GeoHash a little bit more. In Redis GeoHash, so if we have to use this Redis GeoHash, of course, like from some kind of a mobile application, we are going to call, right? So suppose I have a mobile application here, and this mobile application, sorry, and this mobile application is going to call my Redis GeoHash. And how are we going to design it? So while designing anything around the mobile application, so we need to keep a track of users location change. This is very important because suppose a user is currently standing in Mumbai, and he plans to go to Nasik, and you keep on showing in your mobile app the user who is standing in, like who is in Nasik right now, the old stale nearby businesses of Mumbai. So your nobody will be using your app, right? So in that case, one of the very important thing is we are going to keep track of the user's location change. And in case like in any mobile development scenarios for Android, what we are going to do is like in a little bit older application, they used to use the broadcast receiver. And using broadcast receiver, you could actually listen to the location change event, and based on that, whenever this location change is being fired, or some kind of a latitude longitude change happens, you can actually fire up your query on any location change event. So any kind of location change happens, you can fire a query to the uh, fire a given query to the geohash. Now, in modern applications, instead of broadcast receiver, we are using fused location provider client. So this is a way more modern version than broadcast receiver, but yeah, it kind of does the same thing. Like it helps you to listen to the a location change event. Now for iOS, what we can do is, in iOS, if you are a developer and you want to do something around the location change, the similar kind of things like fused location provider client, we can do via CL location manager. So CL location manager is again one of the interface that iOS gives you natively, which can listen to the location change, and based on that you can fire up events. So now let's talk about now that we know about some of the low level designs, how what will be the basic API calls like we discussed at the very start, right? What are the different API calls that we are going to make for this, like get nearby business, and also what are the data that we will be posting. So we do have some data, some idea now around the database, around the different low level implementation that we need to do. So let's discuss about the final the scale, availability, and final design, how the final design would look like. Okay, so now we will discuss on these terms. So what will be my backend data model, like how I'm going to store the data? So let's talk about few of the geohash, few of the considerations like this. So one thing we can do is we can create a NoSQL structure sort of a thing. And what we can do is, suppose this is my geohash, this particular data that we see over here, sorry, suppose this part is my geohash, right? This is my geohash, and this data that I see, these things are my given business id, and the business id in turn will be stored in some other table. So a singular geohash can store something like multiple data like 349, 350, 351, and so on. But there is a catch to it, like every time I need to update this. So how the update will happen is, I need to take this whole row out. Like if I have to update it, I need to take this whole row out, and then I need to edit this out. So in a relational approach, a better thing to do is taking all the data into a separate business id. For example, something like this. Yeah, this is the data, sorry. Yeah, sorry. I was unable to copy this data. So you can see like each of the data we can do it in different row. So in that case, what will happen is, in case I have to update any given geohash, I do not have to take the whole data into the memory and update it. So this is a way here we have to scan the entire array, and the other like the other consideration will come, right? Scanning and then inserting, and sometimes even the row locking might be required. But here, as you can see, like all those consideration need not to be taken. We can just keep on simple addition and the removal we can do. So here, if not only addition, even the removal can be expensive operation going by this one. So even the concurrency, handling this kind of concurrencies are very easy. So this is again one of the lesson that even if something looks fancy on a single go, but we always have to think in terms of the crude operation, whether they might pose any concurrency challenges or any locking challenges in a given situation or not. So now let's talk about the actual scale. So if we are storing the business IDs into a different place, so for example, 343, suppose it is some cafe in Mumbai, cafe 1. 347 is some eateries, some other eateries, right? Eateries 2. Then all these details are completely stored in a separate table, and this table will be indexed around the geohash, and here this table will be indexed around business id. So the main thing is that this data will not be very huge. In case we do some kind of a, like we come into some kind of a calculation to see the size of the database. So let's talk about the estimated size of this this database. Okay, this data can be a little more, but our main index data, when we are seeing, suppose the number of businesses are like something like yeah, 1 million or so. Okay, so average geohash length is like 6 bytes for geohash, and the business ID length is 4 bytes, right? For biz ID. Now, the total size will be like, even if I am doing something around 10,000 to 10,000, yeah, if I'm converting into this and multiply into 10 10 bytes, the size is very nominal. Okay, even if you are considering all the other details, so like it will probably hardly cross like 1 GB or 2 GB, which is quite okay to hold in a single single shard database. But the only problem that we might face is like the write is very infrequent here, right? So there will be hardly some businesses will be added per seconds, or which can again be very, like, even if it is a per second business addition, it is very easy to handle by any given database. But the read queries, the read load can be heavy, because around the world people might be keep on changing their locations, and we have to keep on getting the businesses of different radius. So in that case, what we need to do is we might need read replicas instead of shard. The simple read replicas will be enough. So let's try to formalize this thing into our this database, how this database would look like. So suppose there is a given user. Okay, that given user, uh, here is a here is a basic user is standing over here. So this user will be basically hitting to our database. So instead of database, what we primarily have to do is the database that we have over here, instead of directly hitting the database, because the business ID business ID we should sync with our whenever a business ID is being entered, it can take some time to reflect. We can take that luxury. So instead of going over here, what we should be rather doing is we should take it to take it via Redis. Okay, so there will be a syncing mechanism between Redis and our database. And our database, what it will have is, our database will have some read replicas. So the reading will have from this read replicas, and there will be one primary database, and of course there will be this will be replicas. So I will make this better drawing right now, but before that, this is just to explain you. And of course, before coming here, probably we would also need a load balancer, because the database, he will not be directly hitting, right? Before hitting to the database, he will be hitting some kind of a this Redis layer, and this Redis layer will be served via our APIs. So we have to see, like, via the rate limiting and the other parameters, what will be our load balancer, our LB logic. So this will be on a very high level, a rough sketch of what we are doing. Now let's totally formalize it into our actual design. So we will draw it for you. Yeah, so there is a user. This user, what he will do is, in our system, he will at first hit into our load balancer, and based on that load balancer load, we will be divided into a different of API endpoint. Suppose he's doing some kind of a location search in Europe. So Europe will have a separate kind of a API server, and whereas the US or the Canada, they might be having a separate kind of a API server based on the load balancer. This division will happen, and then what we will do is from our Redis cluster, from our Redis geohash, we will keep on reading the data for any location. So we are going to pass like the search nearby and maybe a given radius. Based on that, we are going to read that data and return to the user. And here, this business endpoints, what it will do is it will keep on updating the primary database. Any new business a given person is updating or adding, he will be updating it to the primary database, and there will be a replica databases, and this replica databases will be used for syncing with Redis cluster. So the moment this data comes, probably by eventual consistency or some kind of a consistency level, we will going to replicate into this two database. And once this is getting replicated, some kind of a sync we will have to if sync or CDC, when I say CDC means change data capture, we can use tools like Apache Airbyte, and we can capture what exactly is the change of that. What exactly is the change of this particular data set has happened, and we can reflect it back to the Redis cluster. So sync or CDC, like sync mechanism or the CDC, we can use here. And this is how we can very easily, I mean, all this discussion that you see, it comes down to this three level of diagram. So overall, this is a pretty easy system, I would say, when we have to, in case we are actually done with all the decisions, whether we are going to use Quad Tree or Google S2 or Redis geohash in other case, and what kind of consistency we need. Like definitely the business, the business endpoints doesn't need to be reflected immediately, so a Redis is a perfect choice. So as you can see, like this comes down to a really simple diagram, and in this process we have learned multiple things, like what would be our given API endpoints, what are the data model for storing different data, here we have discussed the basic data model, and of course the three main giant algorithms or techniques for storing any geohash based, any geographical or the location based data, that too we explored. And yeah, this is then we come up with the final diagram. Thank you very much for uh, listening to this. In case you have any question, please put it into the comments. I will try my level best to explain it. Thank you very much.